All right, welcome everyone to the last QtDay talk of the day. We're about to watch the recorded keynote on Qt containers and algorithms presented by Thiago. So let's go ahead and bring Thiago live so that you can say hi to him before we get started. Okay, there we go. There you are. Perfect.
Hello, everyone.
Hi, Thiago, and welcome to
Hello.
QtDay. Good to have you here.
Good to have you too.
Excellent. So let's talk about Thiago here. Let me tell you about him. He holds a double degree in engineering and also an MBA. He has been involved in several open source projects for nearly 20 years, and he is an experienced C++ developer. He's been involved with Qt and KDE since 2000 and was the author of quite a few classes in Qt Core, Qt Network, and the entire Qt Bus module. And he's been the maintainer for Qt Core since 2012. He currently works for Intel's System Software Products Linux team, where he is a software architect for the Clear Linux software project for Intel architecture, with responsibilities including expanding Clear Linux to new segments and uses. So here's a little bit about this talk. Qt has always been come with its own set of containers, including QString, in addition to what the standard library provides. So what containers are best for each task? When should I use the standard ones? And what advantages do the Qt containers possess? And so these questions will all be answered in this talk. So thank you for that. All right, everyone. So we're just about to watch the video, so please stay tuned until the end for the live Q&A with Thiago. And I just want to give everyone a gentle reminder that if you do have questions to ask, so next to the room chat, there is a question mark button. It's not the help button. It's actually the Q&A chat. So please ask your questions there, and then we'll answer them at the end. All right, see you very soon.
Hello, everyone. Welcome to the Qt Containers and Algorithms session. This is the first for me, I don't know if it is for you, where we have a recorded session. I've never done this before. I've done remote virtual presentations, but never recorded before. So you don't get to ask questions to me right now, which I usually allow during the presentation. But I will be live during the transmission. So when the presentation is transmitted, I will be there, so you will have the chance to ask me questions. So for those of you who don't know me, my name is Thiago Macieira. I am the maintainer for Qt Core. I've been developing with Qt for 20 years, and I've been developing Qt itself for 15. I started at Trolltech back in 2006. My first big contribution, was the Qt Bus module, for which I was maintainer for a long while. And since the beginning of the open governance of Qt, I've been the Qt Core maintainer. I continue to be that. And my role today in the Qt project is to help it move along. As you can see from the slides, I work for Intel, and at Intel my work is not related to Qt at all. And if you ask me what I work in Qt, it's also anything that isn't graphical. And that was the title of my presentation last year at QtDay, when I presented a session called Everything But the Graphics. So my work doesn't take me anywhere near graphics. My work at Intel is related to servers and to high performance CPUs. And I spend most of my time looking at code, trying to make it better, to make it more optimized, which I also experimented with Qt and tried to do some optimizations in things like getting containers more optimized, better code, better cache locality, more efficient algorithms for conversion, for copying, and things like that. So, and this brings me to the session today when we're talking about containers and algorithms. I'm not going to talk a lot about algorithms today. I'm going to talk more about the containers. If you have questions on what we can do with algorithms, we can always talk about them. But we're going to focus on the containers and some of the things that they can do. Before anything, I imagine some of you have a question about why does Qt have containers at all? So for Qt 1 through 4, the reason is mostly historical. So it happens that Qt predates the standardization effort of the C++ language. There was no standard library when Qt was first created. When Qt was first released in the middle of the 90s, there was no such thing. There were several STL port libraries. There were several STL libraries that you could use. But the quality that they had varied quite a lot. It was not very good for us to depend on it because some compilers did not support it at all. So we couldn't depend on the library being present. We couldn't depend on its quality because many of them had poor implementations of algorithms, poor memory efficiency, and that caused that applications, if you really depended on them, had very wildly changing characteristics at runtime depending on the platform that you ran on. Also remember that up through Qt 4, the middle of the Qt 4 series, we still supported quite a few of the commercial Unix operating systems, such as IRIX, HPUX, AIX, and Solaris, where it was just very, very different. Today the situation is different because since we only basically support Linux, Mac OS, and Windows, we can control more what goes into them, and we know the quality of the libraries that exist. I just want to mention, I mentioned these big three. Those are not the only ones. There are others that are supported, such as QNX, Integrity. I know Qt runs and compiles on FreeBSD because I try it myself. But the big three are Linux, Windows, and Mac OS. And Mac OS derivatives and Linux derivatives, of course, like Android, iOS, and things like that. But if those were the reasons for Qt to run through 4, why do they still exist in Qt 5 and 6? Right? So the reason for that is compatibility. There is just way too much code that developers like you have written that is done with the Qt containers. Removing them would be would break everything. And I don't exaggerate when I say everything. Because the Qt APIs use the containers themselves, we would either create inconsistency by beginning to port, or we would just break everything and we have to have a flag day to change from one to the other. For those of you who were part of the Qt 3 to 4 porting effort, you may remember how difficult that was because, among other reasons, the containers changed. That's when we got rid of the old QPointerList and QValueList as example containers into the simpler QList and QVector. And among other things, that caused compilation to be very difficult. It caused code to have to be ported one day and not moved to the other. The migration from 4 to 5 and 5 to 6 has to be much simpler, otherwise people just turn away from Qt. Another reason is, of course, the API. The API is designed for humans. That's how I like to call it. When you say something is called push back, which side is the back of the container? Is it the beginning or is it the end of the container? The lower indices or the higher indices? 0 or the size? I ended up having to learn, memorize that push back is at the end. But why is the end the back? Doesn't make any sense to me. Whereas append, for me, always means add to the end, right? Prepend, you do this for other things. You append and prepend to, that's a concept that exists before. So the API being similar to the rest of Qt, the same naming convention, the same consistency in naming so that it is intuitive, applies to the Qt containers, and that is not the same as the standard library. And then there's, of course, the implicit memory sharing. It is not something that you see in the standard library, and there are quite a few people who dislike the Qt containers for having implicit memory sharing. They do produce, unfortunately, some unexpected memory allocations if you're not careful. On the other hand, implicit memory sharing, which is done with a copy on write, does make it simpler for developers who are just beginning with the C++ language. Of course, we needed them before C++ 11 because we didn't have move semantics, so using containers without implicit sharing caused copies all over the place. With move semantics, it means that one container can hand off the contents to another without causing memory reallocation. But this was never a problem for Qt containers because they've always done implicit sharing, or at least have since Qt 3. So for developers who are also not very familiar with the C++ language, it is useful to have implicit memory sharing because really it allows them to avoid pitfalls and mistakes. So on the code that you can see here, and I don't have a way to point to the slides so you can see them, this function is taken from existing code in Qt. So this is actual Qt code from QObject, the function called dynamic property names. It returns a byte array, a list of byte arrays of property names. And it returns a list. That's it, right? So what happens if this were a standard list or standard vector is that it would have to copy. So all of the strings in this list would have to be copied because there is no sharing. In this example here, as you can see, it doesn't copy because of the implicit sharing. You may raise your hand here and say, well, you can avoid this by returning a reference or a const reference to the internal list instead of returning a copy. As you can see in this example, there is a condition in which there is no list yet. Because it is dynamically created, it's a lazy creation of a list, the structure in which the list may exist is not created for every QObject. We need a way to return an empty list without binding a reference to it. So this is the solution we came up with. It is much simpler for us to do this and not having to jump through hoops. And especially this is important for developers who are just beginning with Qt and with C++, of which there are many, and they don't understand the pitfalls of memory sharing. However, one of the things we've begun doing is use the standard library in our implementations as much as possible. So this is taken from QMap and QMultiMap in Qt 6. It's not the case in Qt 5, but it is in Qt 6, that both classes are just wrappers around the standard library classes map and multimap, which have roughly the same semantics, but with an internal shared pointer. So they implement the implicit sharing on top of the standard library container. There is an unfortunate trade-off here, in the sense that in order to implement this, we add a level of indirection. We had to choose either we rolled out our own containers and then had implicit sharing, or we used directly where we got rid of the implicit sharing to use the memory, the standard library, or we introduced an indirection in order to have both the Qt API, the backing of an existing efficient implementation from the standard library, plus implicit sharing. So unfortunately, you can't have all three. You have to choose two of the three, and we chose for this class, for QMap, because the performance requirements are not as great as in the other containers we're going to see. The trade-off was acceptable. Now let's take a look at the container list, right? So these are the containers in Qt, especially Qt Core. I've highlighted the big ones. The ones that you're going to see everywhere in Qt are QList and QVector, QString, quite a bit of QByte array. The other ones are much less common. Yes, you're going to use QHash and multi-hash, QMap, etc. You're going to use some Latin one string views, and things like that. But by far, you're going to use QList, QVector, QString above all else. Let me just point out a couple of things. The ones that you see in italic on the right side, the QByte array view, QString view, QUTF string view, they are views, they are not containers. We're going to get to the distinction for them later. QLatin1 string should have been a view, but it predates the concept of views in the C++ standard library, so it doesn't have the same name convention as all the other ones. We might just introduce QLatin1 string view for completeness for porting code going forward. Anyway, let's go over some of them. I'm not going to go over all of them, but I'm going to go over some of them. And I'll make a pause between switching slides. I don't know if we can do during the presentation, pause the video so you can ask me questions, otherwise we can get to at the end. Okay. So the first one is QList and QVector, which I said is the most, by far the most common container you're going to see. And the first question you're going to ask is, which one should I use? Well, in Qt 6, the answer is very clear because the two are actually the same class. One is just an alias for the other, again, copied from Qt 6 source code. You see QList and QVector are the same. Let me also make a parenthesis here and mention that QList is not like the standard list class. QList is equivalent to standard vector, which is why the two classes in Qt have the same, or the implementation, they are the same class. So they are sequential containers and have contiguous memory allocation. So one element follows the other, there is no gap. You can do pointer calculations between one element and the other, and you're guaranteed to find the next element in the sequence, right? It is not a linked list. So yeah, for Qt 5, before Qt 6, if you have to make a choice, if you have to choose for a code that happens to both, the suggestion is just use QList. The performance is not that bad. It is acceptable. It is the standard going forward for us. We are calling everything in the Qt 6 API just QList. So this is what you're going to see everywhere. But you should choose QVector where your performance requirements are relevant, where they are important. You probably should benchmark and find out if QList is a bottleneck for you or not. The reason for that is, again, that QList Qt 5 is not always a contiguous memory. It might be an indexed memory, so it's a different story. As you can see on the right here, I've put this card for every single container. I'm listing some of the properties and some of the complexity, algorithmic complexity for the containers. For QList and QVector, for QVector especially, insertion at the ends and in the middle is linear, ON. Because of we do some pre-allocation at both ends for QVector and Qt6, only at the end, at the tail end in Qt5. The cost is actually amortized, so if you keep appending, you're going to hit the linear complexity requirement only every so often. All of the rest is going to be O1. The important thing is that random access to any point in the list, in the container, is going to be constant time, O1. Right? That's because they are indexed, right? The index is a number from 0 to size -1. There is no reordering. It's not sorted at all. It retains the insertion order. So if you append, the order of the elements as you can read them is exactly that which you appended at. I mentioned that QList is not a linked list. If you want a linked list, Qt5 had QLinked list, which, as the name says, is a linked list. It is a sequential container, but it's not contiguous memory, right? So it is node-based. Each element from one to the next, it might jump elsewhere in memory, which is usually not good for cache locality. You incur some cost in that. The overhead is bigger. And since it was so little used, almost never used anywhere in Qt code and almost anywhere in client code, we just decided to drop it. It is still available in the Qt5 compat module in Qt6, but we just recommend that if you need it, use the standard library. If you for some reason need some of the properties, which is it guarantees that insertion anywhere in the list is linear time, right? It's not linear, it's constant time. Insertion at the end or insertion in the middle is constant time. If you need this property, and if you do, you should probably know it by now, then use the standard library, use study list. The trade-off is, of course, that random access to an element is linear time, right? That's because you can only iterate forward. You start from the beginning and you search all the elements until you reach the one you want. So it is not an indexed list. You can't access elements by index. Some of the earlier pre-Qt4 implementations had an API that was linear access like this. This doesn't exist in Qt5 anymore. It doesn't exist in Qt4. It doesn't exist in the standard library. But like QList and QVector, the insertion order is retained. Again, so if you append, when you iterate forward, you get exactly the same order you had when you appended. The next set is now not a sequential type of container. It's QMap and QMultiMap, right? They are simple containers that associate a key value to a value, right? So a key to a value. They are not contiguous. Qt does not offer a contiguous associative container type. If you really need this, I think that the standard library has one, or you can roll out your own by using QVector of pairs or QVector of tuples of your own structure. You can always do that. You should use QMap or QMultiMap as opposed to hash and multi-hash, you're going to see in the next slide, when the key order is important, right? So unlike the previous two that we've just seen, QMap and QMultiMap do not retain insertion order, right? They are ordered by themselves. They sort, actually, by key in ascending order. So they are indexed by key, and they are ordered in ascending sorting order of the key. That implies that the key type must be comparable for equality, so two keys need to be checked if they are the same or not, and they must be orderable. And more important than that, they must have strict total order. Right? They mustn't have elements that are unorderable, because that's just going to break the internal logic. All of the elements must have the operator less than. QMap and Multimap do not support using a template parameter to change the equality comparison. I actually think that we use QList. I need to check the implementation to be certain of that. Just a quick on the algorithmic complexity. They have logarithmic insertion and random access. This, of course, will depend on your standard library implementation. I think that it requires the same thing about insertion and random access. And the reason for that is, again, that they are sorted. And because they are sorted, they can the search for the point where a key is or should be can be done by binary search. So you do that, and you get log 2, base 2 of the number of elements. That's the number of comparisons that you must do in order to reach the point where the key is or should be. And you conclude whether it exists or not, and you can insert that point. Now the other half is the QHash and multi-hash. I'll get to why the multi in a second. But compared to QMap, QHash usually, not always, it's not guaranteed, but usually can do constant time searches. So it implements a hashing table. What is a hashing table? A hashing table is basically a set of buckets where we pass the key type through a hashing function, which you can see the prototypes for here at the bottom, which changed, by the way, in Qt 5, in Qt 6, right? If you forgot to update it, that's no problem. The one in Qt 6 just has more bits. And it does that by applying this hashing function that returns a number, and by that number, it allows us to know where, which bucket the element should be in. Because it is a reduction function, it does not have to have perfect order. Different elements can have the same hashing function. That is why it's not guaranteed to be constant time, but it usually is. And when it isn't constant, it is fairly close. It will do one or two more comparisons per search. Unless, of course, you have a degenerate hashing table. And in order to avoid having a degenerate hashing table, Qt applies what is called salting. So every time you launch your application, the mapping of buckets, of elements to buckets, changes. Which means that not only is the order of the elements arbitrary, so they do not retain neither the order in which you append, or in case insert the elements, nor are they sorted by key for any type. And moreover, if you run the same application multiple times, you might end up with a different order every time you iterate. So if you need to depend on your application's output should have to be consistent, this is when you choose map instead of hash, because that guarantees consistent, predictable results every time you run it. A hash will not guarantee you that, which is a benefit if you look at it, because it prevents an attacker from knowing the order and therefore causing your hash to become degenerate. I mentioned that why are there multi-classes instead of just the beginning one? The multi-hash and multi-map classes, unlike the non-multi versions, allow you to insert different values for the same key. It's like if you had every single element was a list of itself, and then you could iterate over each of them. They just have a more convenient API. This is common in many situations where one key can appear multiple times in an associative container. Not always. So if you look at, for example, JSON or other serialization formats, they require that a key appears only once, and if they appear more than once, the table is wrong, right? The format is probably corrupt. Another one that is an associative container, right? So it's associative, is QSet. The reason it is associative is that it is actually implemented using QHash, but it associates a key to nothing. That's how you call it. It is basically a set of keys, and it allows you to keep the set of keys without duplication. It will prevent multiple keys from appearing multiple times. It has a cost associated with it, and sometimes there are better alternatives than QSet to do some high-performance work of deduplicating keys or verifying whether a key has been seen or not. But for simple code, this works, it helps, it is there, and we have functions to do conversions from list to set and back, which causes removal of duplication. It also changes the order, right? So if you go from list to set back to list, it will remove the duplicates, but it will also randomize the order of the elements in your list. It inherits the properties as QHash, associative non-contiguous, usually constant time insertion and access. There are two more that I want to talk about, which are QStack and QQ. They are not actual containers. They are adapters on top of QList and QVector. There are standard library equivalent classes called studStack and studQ, if I'm not mistaken. They are actually adapters. So they contain an item, a container which you can specify as a template parameter. The Qt versions do not have that. They are really just on top of QList and QVector. They are a QList or a QVector in this case, which means that you could access the other functions that allow you to do insertion in the middle, random access. I wrote here that it is not allowed. You shouldn't be talking about this, because if you are using these classes, it's because you want to use the dedicated functions for them. But they exist. So what do they do? A stack implements the last in, first out policy. That is, you put one item on top of the other, and then you undo that. That's a stack. And a queue is, everybody knows what a queue is. You have each one going the first in, first out, allows you to do that. There's also other classes like QHash that implement least recently used least recently used policy of eviction and things like that. I'm not going to go into them. The last one that I want to talk about, the generic containers, is QVar length array. It exists for one reason only. It is that it allows you to use pre-allocated memory, usually useful in a stack, right, in a function scope, which means that you just use the stack, and if you go over that limit, then it allocates memory dynamically. Another quick parenthesis, this is the only container in Qt that is not implicitly shared. Because it is very specific of its use case, it usually is used as an intermediate step where you're calculating things that you need to keep a list of, and you don't know the exact value, you just know the typical value, and you want to reduce dynamic memory allocation. You would use QVar length array for this. Right, so it is a sequential container, just like QVector, contiguous, insertion at the end is amortized, random access is constant time, and it retains insertion order. Now let's talk about text, right? So I remember when I was working back in Trolltech, and I remember talking to a colleague of mine who had been given an application from a customer to debug. I don't remember why he had to do this, but we didn't have the sources for it. But we did realize that they were using QString everywhere. So he made this comment that world domination starts with QString, and I completely agree with him. The reason is that it is not comparable at all to studString class. It will be kind of comparable when the Unicode study group in the C++ committee finishes the definition for the standard text classes, but string is not comparable to QString. That's because the QString class has a lot more functionality. It actually is meant for human text. It enforces that the encoding is one particular encoding. It is UTF-16 for QString. You might disagree why it is, but it is a single encoding, whereas studString makes no determination, which means that it is a convention of your application of a library, and you could go wrong when crossing boundaries that don't agree to the same convention. It also has a lot more convenience functions like regular expression, conversion to other encodings, reading and writing, I/O starts with normalization, and all of this which you find in QString and you do not find in studString. We use it for everything related to text and Qt, including some things you might not think are text, but we consider being text, like file names and host names. Right? You saw before in one slide where Qt property names are byte arrays, they're not QString, but for almost everything else, like attributes, like file names, host names, whatever else I can think of course I'm drawing a blank right now, we just use QString for it. It does mean that sometimes we have memory allocation penalty, but then it would just standardize of everything, same API for everything. For these classes, I'm not going to talk about the algorithmic complexity. What I'm going to talk about them is whether they're containers or views, and we're going to go about what a view is when we get to them. QString is a container, right? It means that it manages memory. Its element is a QCar or car16T because its encoding is UTF-16. So you can iterate over the elements, and you get Unicode code units out of it, UTF-16 code units specifically. Qbyte array, on the other hand, is what would be more like studString in the standard library. Even then, we have a lot more functionality that the standard library does not have. It is used in Qt to store 8-bit content whose encoding either you don't know or could be anything. So it could be stored elsewhere, metadata or another variable, something like that. Or it could even be binary content. So with the same class for everything, we use car as the element. In the API, you see that. It should be std_byte. But then because we actually have convenience functions to treat it as text, because it happens way, way too often, we just use car for everything. We also have some convenience functions that do treat it specifically as text and apply an encoding for it, and it is US ASCII 7-bit only. And I think only we have the 2 upper and 2 lower classes that do methods that do that, because again they are fairly common. You do not want to apply Unicode uppercasing and lowercasing everywhere because some protocols will not recognize it. But if you do it on the 8-bit level at Qbyte array, you only get the keys for US ASCII letters, the 26 letters of the English alphabet. We use it everywhere in Qt where I/O appears, so input and output. So file, input and output, reading files, writing to files, network, input and output, so any types of socket. You can talk about Bluetooth as well, same thing. We also do it in serialization, so the backing of JSON value, of JSON documents, byte array, Qtext stream, they all are Qbyte arrays. What did I say before? JSON document, data stream, QDataStream. Right? QDataStream, QTextstream, JSON document, QCBOR value, XML, they are all backed by a byte array and do reading and writing using that. Then we get to the views. So what is a view? What is the difference between a view and a container? A view does not own the memory that it is pointing to. So the memory management is external. Usually it is the matching QString, right? So QString view can point to a QString, and so long as that original QString does not reallocate memory, the QString view remains valid. QUTF-string view and QLatin1 usually point to literals in your code. That's when you use the quote marks and declare a variable. You can use these two to declare that your input is specific encoding. So they're usually used to communicate to QString that your data is UTF-8 or Latin1 without having to reallocate memory and convert into UTF-16. That's because QString has methods that do recognize and operate directly on these two encodings without having to do in-place conversion or memory allocation. So the three classes that you can see here are QString view, that like QString is just UTF-16, it is Unicode. UTF-8 string view, as the name says, is UTF-8. Its element type is car, because we don't have a different type for it, or car8t, which is a new type coming in C++20. I think that the implementation is ready, and the moment that you compile with C++20, if you use U8, quote, whatever it is, it converts automatically to QString, QTF string view. I think actually there are bug reports that this is broken, we need to fix it. And QLatin1 string, if you've seen it before, it has existed since Q4. It expects the encoding to be Latin1, so ISO 88591. And the reason why we chose Latin1 instead of just US ASCII 7-bit is because it just makes no difference to us, right? You can shovel every US ASCII under these two view classes and it's going to be the same, but Latin1 is slightly cheaper than UTF-8 to convert, compare, and others to QString content. Just giving you an example, this is my last slide, on how they get used. So again, code taken from Qt content. This is existing content inside Qt. And you see the first example, the top left says, it is just doing a comparison of a QString to a QLatin1 string. This has been Qt internal library coding policy that we always mark the strings with QLatin1 string because, again, there's a slight performance advantage in not having to convert to UTF-8 or do the UTF-8 conversion. Also because, as you can see on the bottom example, right, our channel is again a QString. In Qt5, it did an in-place conversion, an implicit conversion, not in-place, implicit conversion, which means that it allocated memory to compare out channel to the string literal. In Qt6, it does not, because the new class exists. It just says, this is UTF-8, and therefore we can do the comparison, equality comparison, or ordering, or searching some of the substring operations in QString directly without having to allocate memory. So that's why the Qt4, 5 coding policy, library coding policy required us to mark which strings are Latin1 to avoid memory allocation. And on the top right, you can see an example of an implicit QString view, and you see the letter U before the string. That's the C++11 Unicode string marker saying this is a Unicode string, right? It's already converted into UTF-16 by the compiler, and we just do basically a memcompare here to confirm that the QString is equal to the 0 digit. Right, that's it. So I'm hoping that we can open now for questions. I don't know how this works. I'm hoping that we can, that you've enjoyed so far. If no, there are no questions. And if I don't say this later, you can always contact me by email and ask me questions, and we can talk about how you can apply this to Qt, how our improvements are ongoing. And I'm pretty sure there are probably other people in the audience here who can also answer some questions about the work ongoing in Qt 6. So thank you very much, and let's see about some questions.
All right, everyone, welcome back after that video. We have some time to do some Q&A, so let's bring Thiago back, and we can have any questions answered. So Thiago, let's turn on. There you are. Hi. Welcome back.
Hello.
First of all, I want to say thank you so much for your contribution to QtDay, even if it is virtually this year. We're happy to have you.
Yeah.
For
Hope
sure.
hope that next time we have this, I can be there in person. The trip to Florence was really nice. It's a really nice city. But it's interesting to do all of these things virtually. That has allowed me to go or to present at more conferences than I usually do, because I don't have to ask for a travel budget.
Yeah, for sure. So there are some upsides to that.
Yeah.
So this is a good time if anyone has questions to prepare them. And if you guys are typing that while you're getting that ready, I'll ask you another question, Thiago.
Of course.
If there was anything you wanted to add to your presentation, or anything you wanted to say about your participation, other things you enjoyed or that you're looking forward to?
I'm just saying that this is a nice format. We'll see about doing it again. On the presentation itself, I think that we could stay here for another 2-3 hours talking about containers and containers alone, and just discussing performance. There's a flurry of changes. There are a flurry of changes that we're doing right now in QString, QList to match and exceed performance from Qt 5. So I can point to links, I can get people to do more comments. Just one more detail, I think that in the video I did mention my new role, which doesn't match what you had introduced me as, because I got a new role at Intel since I had submitted the bio.
Oh,
so just
okay.
Small detail.
Okay, great. Well, thanks for updating us about that. Sorry, we still had the out of date bio.
It happens. It happens.
For sure. Well, I'm looking, and it seems that there aren't any big questions. I mean, people were chatting throughout it, but there was just one small thing.
Yeah, we can talk about the discussion we had during the session. It was in the section about being able to return something that was a non-existent or created on demand, right? So the example was there's a condition. If that condition is true, return a container. Otherwise, we have to return something that is created on the fly. And the comment was that we could return a static variable. And that is a good solution. I thought about that during this session, when I was writing the slides as well. And it is true, but I can always complicate the problem, right? So imagine that you don't have, that your API returns something that you now store as the keys of a hash, for example, or just the values of a hash. So you have to return a copy. You cannot return a static because it's a different type. So there are a number of reasons why it is a lot easier for developers who are just beginning with C++ to use the shared copies. than to have deep copies like the standard library. So, and of course, the other way around is also true. The standard library, because it does not do implicit copies, it knows that you know exactly where it is going to cause a copy, if any, right? Whereas in Qt code, it can happen at any point, which means that unfortunately we have more code expansion or slightly more code bloat.
Mm. We have a comment here. Filippo says it's more complex for a SDK developer to make that sort of optimizations.
I'm not sure exactly what Filippo means by an SDK developer here. If you can type down, Filippo, what you meant there, I can try and address it. I think that it is true that if you're using the Qt containers, it takes away some of the optimization opportunities from you in the name of flexibility, in the name of making things easier. I completely agree. But it also makes things easier for those who are not seeking the last cycle of CPU performance. So for those who want to get to the 80%, it's a lot easier. Whereas for those who want to get to the 100%, it kind of becomes near impossible. Okay. So strike a balance there.
Thank you for that clarification. All right, so I don't see any other questions, so I guess we can end early unless you wanted to add anything more.
No, I think I'm good. Thank you for having me. Thank you for putting the event together. It's really nice. I haven't been able to watch any of the sessions because they're in the middle of my night, but I'll try to see any recordings when they come online. Excellent.
Yeah, that's one great thing about them is if you do miss them, you can see them later or rewatch them. That's true. For sure. All right. Well, it's evening here, but I guess it's in the middle of the day for you.
Yeah, I'll be having lunch in an hour or two.
All right. Well, as we say in Italy, buon appetito. Enjoy your lunch soon. And thanks for coming. Hope to see you next time.
I hope to see everybody too. Yes.
All right. Take care, Thiago. Bye-bye.
You too. Bye.
All right, everyone. So that was the end of our day here for QtDay. You can definitely rate it on the agenda page, on the agenda page for QtDay. We always appreciate that feedback. So we'll see you here again tomorrow for the final day of the conference. Here's the rundown. Starting at 11 a.m. Italian time, we have a deep dive into Qt Canvas, again by Burkhard Stubert. We'll see him again, followed by Design Thinking, Why You Should Always Include UX Processes in Your Work. That's by Matteo Forni and Tommaso Bovicini. And that's at 12:10. Followed by, at 1:20, we have Quickly and Effectively Testing Qt Desktop Applications by Claire McRae. And then we have at 2:30, How to Improve Productivity with Qt on Mobile, Desktop, and Embedded. And this is from Filippo Scognamaglio, sorry. And then we have the last talk, which is at 4:50, QML Prototyping, Creating Production-Ready and Reusable Code by Alexandra Bettoni. And then finally, at 6 p.m., we have the closing conference by Matteo Benci, and we'll probably have something special lined up for you, so stay tuned for the end. All right, everyone, enjoy the rest of your day, and we'll see you here tomorrow. Bye-bye.